The last topic in chapter 3, chapter 3 is talking about comparing means and comparing proportions. This isn't really a two-sample test at all, this last section. We are going to be comparing two things, but we're going to be comparing two things in just one sample, okay? When we talked about experimental design, we talked about blocking. And the last topic that we talked about with blocking was a matched pairs design. If you remember, we block to reduce the variability in our, the variability in our responses, right? We put like people together in blocks so that we can see if the treatments are impacting the subjects as opposed to, the difference in the different kind of subjects, right? So the most extreme type of blocking was a matched pairs design, okay? In a matched pair design, each person gets the treatment in a random order. So that's it. That's a matched pairs design. Well, the thing is, though, whenever you do a matched pairs design, you're really just taking one sample, and then each person in that one sample is getting both treatments. And I'm kind of interchanging between experimental design vocabulary and sampling, which I probably shouldn't be doing, but we run these hypothesis tests on experiments. So an experiment with multiple treatments is kind of like a one sample test. That's kind of what I'm saying, okay? All right, so paired data results from recording two values on the same quantitative variable for each individual. So we record two values of the same variable for each individual, okay? Or each pair of individuals. You could also group like people together as opposed to the same person. Mr. Smith, the rockstar JCS math teacher, developed a new method for factoring trinomial expressions. He wants to run an experiment to see if the new method is significantly better than the old method used by non-rockstar Mr. Blackburn. So I'm just teasing around here with the context here. So basically we have two techniques for factoring. We got an old technique and we got a new technique, okay? So the question is, if we want to run an experiment to see is the new technique better than the old, does the new technique cause a higher test score than the old, we need to run an experiment. So here's two different experimental designs. So in experiment 1, Mr. Smith will take 14 kids and randomly assign them to two groups of size 7. The first group will be taught the old method, and the second group will be taught the new method. Then everyone will take the same factoring tests, and their scores will be compared. For example, here's some old scores using the old test, and here's some scores using the new test. What significance test would you run in this experiment, and why? So the idea here is, I got 7 and 7. In fact, I kind of matched them up like this graphically because I put them over top of each other. But the thing is this person related in any way to this person? Are these groups independent or are these groups dependent? Are they linked? And this person that took the old method really has nothing to do with this person that took the new method, right? In fact, if I wanted to, couldn't I switch the order of these data points and it wouldn't really matter at all? This group is independent of this group, okay? So we would use a two-sample t-test for the difference in, I always think in or of, difference of means. We got two experimental groups and they're independent of each other, okay? Example, experiment design number 2. Mr. Smith will take 7 kids and randomly assign them an order of new first and old second, or old first and new second. So now we only have one group of 7 kids, not 14. The 7 kids will learn one of the methods first and take the factoring test. Then they will learn the second method and take a similar factoring test, but with different questions. So in this design, each kid gets both a new and an old. And the random assignment isn't the treatments to the student, but rather the order of the treatments to the individual student. So now, why can't you run a two-sample test? Now our data is paired. These are not independent. I only have one group. I'm trying to say this a lot of different ways to kind of make you understand, okay? And there's a link between these two. I can't take this 89 and put it here and this 87. I can't switch these because these are the test scores for the same person. And we're going to get a more powerful test because these two kids were obviously a little bit better at math, so both of their scores are higher. This kid was not quite as strong as math. Their scores are both lower. But the pairing of these individuals reduces the variability amongst the groups. So like, for example, up here, you see how you got all this variability? Because these kids have a lot of different math abilities. But whenever you do a matched pairs design, you kind of reduce that individual variation. So it's going to give us a better comparison, okay? The groups, excuse me, are not independent, okay? So we're going to run a one sample procedure. What experimental design is more powerful? Number 2. Why? We reduce the variability in the responses by I'm going to say by pairing the treatments. I don't know if that's a good way to say it. We reduce the variability in individual students. I'm sorry, I'm fumbling with it. We reduce the variability across different students. I'm sorry, I'm not the best at wording these types of things. I tried to explain it up here, right? Up here, you have a lot of variability in the treatments, right? And that variability isn't just because of the treatment. The variability is because this was probably a good math student, and this one was probably a math student that wasn't so good, right? So that variability is working against us whenever we compare the groups. But in here, we're reducing that variability across the groups because each person is doing both treatments and each person is the same person. Hopefully that explains it a little bit. This is definitely going to be more powerful. Paired data is simply analyzed as a single sample. So we're just going to do so technically we're going to do a one sample t-test on the differences or on the difference list. That's one way to kind of look at it, but this is a really common sample procedure. So we kind of give it its own name. We called it a paired t-test and a paired t-interval, okay? But if you want to, you can call it a one sample t-test on the difference list, okay? It's the same kind of two different options. So to analyze paired data, start by computing the difference for each pair. So if I come up here, the first thing I'm going to calculate, I'm not actually going to analyze these two numbers at all. I'm not going to use these two numbers. What I'm going to use is the differences. So I need to create a list down here called the difference list by subtracting these two and maybe getting a 5 or a 6 and stuff like that. And then we do a one sample test on that difference list. Excuse me. So conditions, random. The paired data come from a random sample of the population of interest or a randomized experiment. If it's a sampling problem, then we need to have a random sample. Usually with paired data, we're going to have an experiment, and then we need random assignment of treatments. We got to randomize the order of the treatments to the people, or if it's a matched pair designs with two different people that are similar, then you need to randomly assign the treatments to each of them. If you're sampling, 10% condition, of course, normal large counts. Again, same thing, only we got to be careful here. We need to look at the single difference list. Don't analyze. Sorry, I'm getting run out of room here a little bit. Don't analyze each list. Oh my gosh. Don't analyze the two lists. What do I mean by that? So whenever when I go to check this check, I'm not going to look at, I got all kinds of circles here. I'm not going to look at this distribution. I don't care about that distribution. I'm not going to look at this distribution. I don't care about that distribution. The only one I'm going to analyze are those differences. So we look at this third difference list and we don't look at these two. That's a common mistake. All right, so let's do an example or go through, let's go through the procedure and then do an example. So let's let mu d be the true population mean of the differences. So mu d is the mean of the difference list. Mu d is the mean of the one difference list. So we got to distinguish between the mean of the differences and the difference of the means. So I know, stats, right? Like this is the difference of two means. I take the mean of one list and the mean of the second list, and then I take the difference of those means. This is not that. This is not this. This is the mean of a single list of differences. So it's the order in which you do things. So x bar d is going to be the sample mean of the difference list. S sub d is going to be the standard deviation of the difference list, and n is going to be the number of elements, number of differences in the difference list. So this is just a one sample test where we're wondering if the difference is equal to 0. Is the mean difference equal to 0 against the alternative that it's maybe greater than, less than, or not equal to? Test statistic, this is the same as a one sample test. It's just instead of putting in x bar minus the hypothesized mean divided by the standard deviation of x over the sample size, I'm just putting in the mean of the differences and the standard deviation of the differences. My degrees of freedom is the same. Confidence interval, oh my gosh, this is a typo. That is not right. Interval is x bar d, or here I called it d bar. Okay, so oh my gosh, notation, I'm sorry. So x bar d is the same as d bar. You know, if we want to call it the differences. So here I called it d bar. Here I called it x bar d. I'm sorry. I like d bar. D bar. S sub d over square root of n. But definitely don't use this mu here. That is not right. So either this, or you could put in x bar d. I think I'll just change this to d bar when I edit my notes sometime in the next 20 years. All right, so we're at 13 minutes. I'm going to do an example. Let's start the next video for the example fresh.